What side length would create an equilateral triangle with the same area and perimeter? How about for other shapes? What side length would create a square with the same area and perimeter? What about a hexagon or a pentagon? There is one trivial solution for all these shapes, a side length of 0. But what about other non-trivial solutions? Does one even exist? To implore, let's start with a triangle. Splitting the triangle down the middle turns the equilateral triangle into two right triangles. We can focus on one of them. And now we can use the Pythagorean theorem to find h. In order to use the Pythagorean theorem, we simply need to know what to plug into it. The hypotenuse's length in the theorem is simply the equilateral triangle's side length. We'll call that s. The bottom side of the right triangle is equal to half of s. And the side in the middle of the equilateral triangle is the height, h, which is what we need to find. Now, by substituting the values into the Pythagorean theorem, we have an equation in terms of h and s. We are left with two s squared variables, which we can simplify. Then, to find h, we can take the square root of both sides of the equation. Since the height is a length, the plus or minus in the square root can be ignored. Now we are ready to solve the original problem we posed. What side length results in an equal area and perimeter for an equilateral triangle? Substituting h in terms of s into the area formula for a triangle provides a formula for the area of an equilateral triangle. This formula could be simplified farther, but the s's will be cancelled in the next step. The perimeter is 3 times s. Set these two equations equal and cancel the common factors. After simplifying the radical, we are left with a final answer. Using the formulas provides the same answer for both area and perimeter. This gives us the answer to our original equation, a side length of 4 times the square root of 3. A similar method should work for other shapes. Let's try adding a side, leading us to a square. For a square, the area is s squared, and the perimeter is 4 times s. This problem ends up being very easy to solve, as we simply set 4 times s equal to s squared and divide both sides by s. We end up with a solution, s equals 4. Cool, so we've done this process for a triangle and a square. I would say try the pentagon next, but the pentagon area formula is a bit... well, you can take a look for yourself. For now, let's move on to the regular hexagon. A regular hexagon can be represented by 6 equilateral triangles and has an area of 6s squared times the square root of 3 over 4. Perimeter has 1 s for every side, so for the hexagon the perimeter is 6s. If we set them equal, cancel the 6 and the s, and then isolate the s, we have our solution. S equals 4 divided by the square root of 3. So, we found the sides for equilateral triangles, squares, and regular hexagons that make the areas and perimeters of those corresponding shapes equal. Now let's ask a better question. Is there a pattern? Or will we have to find the side length manually each time when we want to solve this problem? The points of all regular polygons lie on a circle, so to find this answer, let's try taking this problem to its obvious limit. A circle. Instead of side length, radius will be used. As is familiar by now, the area and perimeter formulas are used. Set them equal, divide common factors, simplify, and solve. A circle's perimeter equals its area when its radius equals 2. Instead of continuing on with a heptagon, octagon, nonagon, and on, we should look for more patterns. There must be regularities. So now with our understanding of the problem at hand and what solving it looks like, let's try to solve for a general solution of any n-sided regular polygon. Start by constructing a regular polygon of n sides. Let's take our n-gon and split it into triangles, as we do. The area of the n-gon is n times the area of one of its triangles. The perimeter is n times the base of one of the triangles. This means that the area and base of each triangle must be the same. If the height of the triangle is 2, it will cancel with a 2 in the area formula, leaving a result of b, the base. This makes sense considering how the circle had a radius of 2. Now we know that the height of the triangle is 2, but how can that help us find b? Let's split a triangle in half to get a right triangle. After labeling what we know, the Pythagorean theorem won't help. There are too many unknowns. But we also know the angle, and trigonometry will help here. The tangent function in particular. The tangent of the angle theta equals the opposite side to an angle in a triangle over the adjacent side. Substituting variables into that relationship leads us to tan of theta equals b divided by 4. And there are n triangles making a full rotation of tau radians. The angle theta is therefore tau divided by 2n. Multiplying by 4 gives us the side length for our solution. Therefore, the side length of any n-sided regular polygon is simply 4 times the tangent of tau divided by 2 times the number of sides.